Check it out now, y'all.
NanoHub U, online instruction.
So, welcome to Module 2.2. And just to remind you what we did in Module 2.1 is that, the overall objective of this week is to introduce a model for calculating this density of states. And in Module 2.1, I introduced this simple model that we'll be using, which starts from this energy-momentum relation. That is, given a solid, we know from experiments from other theory that electrons in the energy range of interest behave as if they have this a particular energy-momentum relationship. So let's say that's given. What we are talking about is, from that energy-momentum relation, how do I obtain a density of states? And as I mentioned, first step is to ask how many states do we have for electrons having all possible momentum up to a maximum value of P. And what I argued in that last module is that without going into any details, you'd expect that that quantity should depend on P to the power the number of dimensions. Because if we are in 2 dimensions, it will depend on this area of a circle whose radius is P, and so on. So that's this A, P to the power T. And we didn't talk about this constant in front. And we said, well, even without knowing that constant, the point is what you see is the overall picture, namely N of P. You combine with E of P to get N of E, and then you take its derivative, you get density of states. Okay. Now, what we are going to do in this module is talk about how to obtain that coefficient that I wrote down. Okay. Now, consider just a one-dimensional conductor for the moment, and electrons can have any momentum, let's say, from minus P to plus P. There is a maximum value plus P, minimum value minus P, and we want to count the number of states. And basically, the number of states you count by saying that electrons can have certain values here, certain values of momentum, and one then tries to figure out how many of these allowed values are contained within this range. Now, classically, of course, the electron could have any momentum. So in that sense, the number of states would have been like infinite, because it will be just continuously distributed. Now, the way you get a finite number is by invoking the wave nature of electrons. And this is the part that would come kind of naturally if you were using a wave equation for electrons, like the Schrodinger equation. And that's the kind of thing we discuss in the second course. Now, what I'll do here, though, is we'll use a very simple model to account for the wave nature of electrons. And that is this idea that I'm sure you have heard of this in freshman physics, that electrons with a momentum P act as if they have this de Broglie wavelength. So I'll put a dB here to denote de Broglie, because after all, I've already used lambda for something that is physically completely different thing, namely mean free path. And this has nothing to do with mean free path. Mean free path is a classical concept. That is particles, how far they travel before they get scattered. This is a quantum thing. It's this wavelength of the electron. And this de Broglie wavelength is related to the momentum by h divided by p. So a given electron with a momentum p has a de Broglie wavelength given by this. Okay. And then the way you argue that momentum can only have certain values is by saying that if you have a box of length L, then you see the electron wavelength must fit into this box. Kind of the way classically, if you had, say, a guitar string. So supposing this, instead of being a box containing electrons, was actually a guitar string on which you could have acoustic waves. Then as you know, like on a string, usually you could have acoustic waves with any frequency or wavelength. But once you pin it down at the two ends, that's when the acoustic wave must fit into that length, which means its wavelength must fit into this box. And that's what gives rise to these specific values of wavelength, which translate into specific values of frequencies, which is why a guitar string has certain resonant frequencies. So, of course, electron waves are totally different from acoustic waves, very different things physically, but the math is kind of similar. The idea is kind of similar. And what you say is that the electron wavelength must fit into this box, and so we can say that the length of the box must be equal to some integer, I'll write that as nu, some integer times your de Broglie wavelength. So the length of the box is integer times the wavelength, because it must be, say, certain number of wavelengths long. Now, if you turn that around, we could write this as, from there, we could write it as P is equal to integer times H over L. So all I did was took the P up here, brought the L down there. And that tells me that the allowed values of momenta are integer multiples of H over L. So when I have a range of P's like this, the allowed values of P will all be spaced by H over L. That's it. And now you see I can count how many allowed states I have, and thereby I can evaluate that function I defined earlier, this n of P. So let me move this out of the way. Just write that here. Take this off. So how many states do I have? Well, n of P is equal to, the total range is 2P, and you have divided by H over L. So that's equal to P over H times 2L. So this is the result for n of P in one dimension. So as I had said earlier, in one dimension we expect it to be proportional to P to the power 1, but now we also have the constants that go with it. Now you could do a similar calculation now, if you want, in two dimensions. So in two dimensions you could do something like this. So we now have this Px and Py, if you will, in two dimensions. And the allowed values are spaced along x by H over L. And you could make the same argument in the y direction and say that in the y direction they are spaced by H over W. And so each state takes up an area that is H over L in this direction, H over W in that direction. So if I want n of P, what I should do is take the area of this circle, pi p squared, and divide it by the area occupied by one of these states, which is H over L times H over W. And this, you'll notice, comes to P over H whole squared times pi L W. And these results are all summarized in that slide. So you can just look there. You see the three results. The ones we have gone through are the one dimension, which is P over H times 2L. And we just went through the two-dimensional case, which is P over H squared times pi WL. And if you want to do the three dimensions, that also follows similarly. Only thing is that now you have to think of a sphere, you see. And when you think of the volume of a sphere, instead of pi p square, what you'd get is 4 pi over 3 p cubed. And in the denominator, you'd have h over L, and then h over width in one direction, and then times h over width in the other direction, which you could write as h squared divided by area. And now if we again just simplify it a little, it will look like p over h whole cubed, and then 4 pi over 3 AL. And that's the last one item up there. That's the three-dimensional. So this is the basic result that we were trying to obtain. And you'll notice then, of course, when going through this algebra, especially if you're seeing it for the first time, it's easy to get too buried in the details to get the big picture. And the big picture is that classically electrons could have any momentum. In order to get a countable number of states, you invoke this wave nature of electrons. And the basic idea that waves have to fit into a box, that is, the wavelengths have to fit in there. The same principle that gives guitar strings specific resonant frequencies and doesn't allow it to generate frequencies other than those specific ones. It's a very different physics though, but the math is similar. Now there's one little subtlety I should mention here, and that is the following. And that is that usually when you talk about a guitar string, you insist that the electron half wavelength fits into a string. Namely, that, namely that the electron wavelength the minimum one would be like the half wavelength fits in, or you could have the next one, which is this. Now, but the way I did it though, you'll notice, is we said that the length should be some integer times the wavelength, rather than put a half wavelength. So I did not have a half here. And this is where I should mention that you can kind of do this in two ways. One is you could use this half there, but in that case, when you count states, you should only be looking at positive momenta. Only this part of the thing. Because when you look at a thing like this, if you wrote the actual equation for this, it would be like, say, sine px type of thing. And sine minus px is essentially the same function. So a minus p and a plus p, you don't really talk about minus p's in this picture, you just count this much. On the other hand, the way we did it, we took this entire range. And that corresponds to what people call periodic boundary conditions. Namely, that is, instead of thinking of a string that is pinned at two ends, you think of it as if it's a ring, as if the left end is connected back to the right end. So that what you have here is waves that are running around the whole thing. And when it is running around the whole thing, it means you could have a plus p that is running in one direction and a minus p that is running in another direction. And so you count the entire window. But now, of course, the states are, you don't include the half here. Now, regardless of how you count it, finally what you get for this function will look the same. In one case, you will count the entire range 2p and divide it by this h over L. In the other case, you would just count a range of p, but then you would use only half of the states would be spaced much closer because it would be in multiples of half a wavelength. But however you do it, the final result is the same. And this periodic boundary condition, this idea that, okay, here's a solid, and you think of it as if the left end is connected back to the right. That's this what's called the periodic boundary condition. And that's very widely used. And you might say, well, that's not really right. After all, this box looks much more correct. You know, there's a electron is more like a guitar string. The electron has to go to 0 at the two ends. It can't get out of the solid. And that's kind of true. It's just that mathematically, it is usually more convenient to deal with this periodic boundary condition. And so although physically that's not what you have, the argument that people use is, in big solids, people use this argument that, well, the actual boundary condition in a big solid does not matter. And so you can use whatever is mathematically convenient. And this is kind of has been used very widely in solid state physics for a long time. Of course, now that you are getting into small things, small conductors, where the actual boundary conditions matter, this is something that one has to worry about in small things. So one very nice example that I'll talk about later is this graphene, which is like a layer from the surface of graphite, which is being studied. And interestingly, it has been studied both in the form of a rectangular conductor, where you might think that you want box boundary conditions, where things stop at the ends. But it has also been studied in a form that's called a carbon nanotube, where it is actually folded over like this, where actually you really have periodic boundary conditions. And when people measure those, what they find is, well, if it's a big thing, it doesn't make much of a difference, whether you're looking at graphene or at carbon nanotubes. But when you look at small things, it does make a difference, because one corresponds to fitting half wavelengths, the other corresponds to fitting full wavelengths, running waves around the circumference. But for our purpose then, the main point I wanted to get across in this module is just how you write that constant that describes the total number of states, because once you have this, then the rest follows in terms of how you obtain density of states.